Hopefully you can see my screen now.
Yes, we can. Looks great.
Sorry. You can see the screen fine?
Yes, perfect.
Perfect. Thank you for the introduction. So my talk today is about nonlinear adaptive cruise control for vehicular platoons. This is a joint work with Professor Iason Karafilis and Professor Marcos Papageorgiou. This is the outline of my talk. I will start with the motivation and the problem formulation. We will see some definitions, some known controllers on ACC systems, on adaptive cruise control systems. We will see some examples and counterexamples. Then I will continue to the main results and a design of a nonlinear adaptive cruise controller, both on open road and ring road. Then we will see some simulations and comparisons, and then I will conclude this seminar. So what is an adaptive cruise control system? It is a system that has a dual operation mode. It extends the standard cruise control and maintains the constant speed for the vehicle in the absence of other vehicles. And it has the second mode, the vehicle following mode, which whenever we see a preceding vehicle, the vehicle switches to a desired spacing to maintain some desired distance from the vehicle ahead. When we place several ACC systems along a string, we have a platoon of vehicles that may reduce accidents, may increase traffic flow and capacity, and may even reduce fuel consumption. Here we will use the following index for the platoon, with 0 is the leading vehicle, with 1 is the first vehicle, 2 the second vehicle, and so on. With SI we denote the distance of between the back-to-back distance between two vehicles. With VI we denote the speed of the vehicle, and UI is the acceleration input of the vehicle. So the core of an ACC system is its spacing policy, how one maintains a desired distance between vehicles. Some very well-known policies are the constant spacing policy, which is a linear function of the distance between vehicles, the speed of the vehicle, and the speed of the following vehicle. And this policy is designed in such a way in order to maintain a desired distance. Another very well-known policy and highly used is the constant time headway policy, which instead of maintaining a fixed distance between vehicles, now the distance is proportional to the speed of the vehicle. This constant T here, capital T, is the constant of proportionality, which is also called the constant time headway. And again, this is a linear controller, which is based on the distance between two successive vehicles, the speed of the vehicle, and the speed of the preceding vehicle. There are also nonlinear controllers. For instance, we have the variable time gap policy, and this is its associated controller. In this policy, we have that the distance between vehicles is not kept constant. It increases as the speed of the vehicle increases, and it is not proportional to the speed, as was the case with the constant time headway policy. And one very good measure to evaluate the performance of an ACC controller is how disturbances propagate along the string of vehicles. For instance, for the constant spacing policy, if we have a leader which has constant speed and suddenly decreases its speed and increases its speed, we see that the second vehicle in the platoon also decreases its speed, but also has some slight overshoot. On the left, we see also the distance of the vehicles. They decrease and increase according to their movement. But as we increase the number of vehicles on the platoon, we see that this overshoot keeps increasing. So for 3 vehicles, this overshoot is even larger, for 5 vehicles even more, and for 7 vehicles we see some very undesirable phenomena. We may have negative speeds, which are unrealistic. We might have very large speeds, which are again unrealistic. We may even have distances that are negative, which imply, of course, collisions. This is what we call string instability, when small perturbations are amplified as they propagate from one vehicle to another on the string of vehicles. A desirable property is the opposite, string stability, where small perturbations are dissipated as they propagate from one vehicle to another, and this is what happens exactly with a constant time head-width policy and its associated controller, as well as with a variable time gap policy. We see here that for the same scenario, the leading vehicle with a black line decelerates and accelerates again, and we see that this disturbance is dissipated along the string of vehicles. The same also holds for the distances of the vehicles. But the issue here is that string stability does not imply safety. We can still have collisions among vehicles, we can still have many undesirable phenomena. For instance, if someone experiments a bit with those controllers we saw earlier, one can see that for some cases, for some scenarios, we have speeds that may exceed the maximum speed limit of the road. We have, for instance, here the road of a platoon of 5 vehicles, a road with maximum speed limit 30 meters per second, and we see that some vehicles exceed this bound until they reach their desired speed of the leading vehicle. Another scenario that one can encounter is in an emergency braking situations. We have here again a platoon of 5 vehicles, and the leader here with the black line strongly decelerates in an emergency situation. Of course, the rest of the vehicles also decelerate, but as we can see here, we have 2 vehicles that have negative speeds. Of course, this is unrealistic and may imply, of course, collisions. Just something that I missed. Here, of course, we have this overshoot over the maximum speed limit, but in practice, we know that ACC systems do not exceed the speed limit because they switch to a desired cruise control mode and they have a fixed speed. But the controller, the constant time headway controller, does not support this switch. Next, we have another scenario which also happens in real life. We have sudden cutting in from another lane where the vehicle also has very low speed. In this case, we see that some vehicles here decelerate very fast, but their distance between them keeps decreasing up until they reach their minimum distance, the length of the vehicle essentially, and go below it, which implies that we have collisions. These are, of course, very undesirable phenomena. And the same can also happen with a variable time gap controller. For the same scenario, we can see that we have distances that are below the length of the vehicles, which imply collisions. We can also have undesirable speeds, which are negative. Of course, with the variable time gap controller, just here to remind you again, we do not exceed speed limits. This is because this term right here on the right does not allow the speeds to exceed the maximum speed of the road. So our question here is, how can one design a controller for autonomous vehicles to have all these properties satisfied simultaneously? We want to have safety, we want to avoid collisions, we want to avoid negative speeds. They are completely unrealistic. We do not want to exceed speed limits for safety. We want to have stability of the platoon. We want meaning that every vehicle the distance needs to converge to some desired value, and also the speeds to converge to some desired value. We also want string stability for the platoon, because this is a performance requirement on the transient behavior and does not allow disturbances to propagate along the string of vehicles. And finally, we also want to see some macroscopic properties for the controller for the ACC system. Now, to see more formally those definitions, what do we mean by the safe the safety on the platoon. Let's say that we have a road with some desired maximum speed, and let's say set the constant A to be the minimum safety distance. We can choose this to be just the length of the vehicle. Moreover, we want to know what are the set of inputs, V0. These are exactly the speed of the movement of the leading vehicle, so we just need the set which describes the speed of the vehicle. Now, we define the state space of the system. This set includes all the speeds which are within the speed limits 0 and Vmax, and all the distances that are greater than the minimum safety distance. What do we mean by safety? We mean that if our system, our ACC system, is initialized within this set, it will always evolve in this set. This will imply that we will never exceed these speeds and we will never have collisions. Similar is also the definition for the safe operation of a platoon on a ring road. We still have a set here. The only difference here is that the length of the road is fixed. The distance between vehicles is bounded by the length of the road over the number of vehicles. Another requirement that we want to satisfy is that this inequality. We want the acceleration of the system, of the ACC system, to be, of course, bounded. This is a very natural requirement, and it depends on the technical characteristics of the vehicles. Another property that we also want to have is that of stability. We want the platoon to be globally asymptotically stable, meaning that whenever we have a desired spacing at the desired speed, then all the vehicles converge to these values. Of course, we can also have some stronger property, like local exponential stability, meaning that if we are initialized close to the equilibrium, we can converge exponentially fast to the desired values. We have, of course, the same requirement on the ring road, but here the spacing is based on the number of vehicles and the length of the ring road. Here we can also satisfy a much stronger property that from any initial condition from the set D, this is the set of safe operation, we have exponential stability. Finally, what we want is to also have string stability for the platoon. Here we use the following definition of LP string stability as defined by Ploeg, Van der Waal, and Nijmeijer, and is treated by this inequality. We use this definition because it encompasses disturbance attenuation here by these terms, and also it adds this term which describes perturbations on the initial conditions. Now, for P equal to 2, the L2 string stability is motivated by the energy dissipation of the system, while the L infinity, here down on the right, is motivated by the maximum dissipation from the desired values, desired equilibria. Of course, if we have this function beta, if our platoon is initialized from an equilibrium position, this function beta is equal to 0, so we have the usual strong notion of string stability. So how do we design a controller to satisfy all those requirements simultaneously? We want safety, we want string stability, and we also want stability. We start by a very general form, which has three terms. These functions f, g, and kappa depend on the spacing between the vehicle I and its preceding vehicle. V is the speed of the vehicle, and W is the speed of the following vehicle. Of course, these functions cannot be arbitrary and need to satisfy certain conditions. For instance, we want the function g and the function kappa to be bounded by this constant k. Notice here that this term on the right gives some dissipation, so this constant k is the maximum deceleration rate that the vehicle can have. Now, what does the first inequality mean? It means that the effect of the speed of the following vehicle is usually less than the effect of the speed of the vehicle I. Here, just to remind you, A is the minimum safety distance. Moreover, we want to have this inequality. This is a technical inequality that will allow us to, of course, bound the speed of the vehicles to be within the speed limits, and also to have a bounded acceleration. Finally, we want this last property to hold, which means the following. If the distance between vehicles is within the constant A and some other constant lambda, then the vehicle decelerates, meaning that the function f and g are 0, so only the deceleration term is present at the controller. So this constant lambda gives us the minimum braking distance that the vehicles can have. Of course, this braking distance is not arbitrary and depends on the technical characteristics of the vehicle, because we want, moreover, we want this inequality to hold. This means that if the braking capabilities of the vehicle are strong, if this constant k is large, then the braking distance can be something small. If this constant k is something small, then the distance between vehicles, the braking distance, should be much larger. Of course, this is a very general expression, but we also want to have some possible discussion on what are the allowable inputs, meaning what are the movements that the leading vehicle can have. Here we have that the leading vehicle should satisfy this inequality. But what does this inequality mean? It means that the leading vehicle should start within this 0 and Vmax, the maximum speed of the road, and can move in any way it holds in this shaded area. It cannot decelerate faster than this blue line. This means essentially that the leading vehicle should not be able to decelerate faster than the rest of the vehicles. So under these two conditions, we were able to prove the following theorem, that this set is positively invariant. The definition of positively invariant set is that if our system is initialized from this set, it remains in this set, the solution is defined for all times and remains in this set. In practical terms, this means that if our platoon is initialized with speeds within 0 and the speed limit, and if the vehicles are not in a collision course initially, then they will never collide and they will never exceed the speed limits of the road. Of course, the same condition also holds for the ring road. The only difference is the set, because here now we have that the space is limited in a ring road. So we also want to have this summation to be equal to the length of the vehicle. Again, we have that this set is positively invariant, and again, we have proved that we do not have any collisions and we do not have speeds that exceed the speed limits. So we were able to design a controller to have safety, but this is not enough to also have stability and string stability. To be able to say something about string stability, we need to further restrict our design. Actually, here we have this controller, which is a simplification of the general form. Essentially, what we do here is we keep the function k as its maximum value kappa, k here. We keep the function g as it is, and we design f based on the function g. So essentially, we only need to design a function g to have stability and string stability and safety, as long as it satisfies the previous conditions. So if we select g to satisfy these properties, we see that these are equivalent to the general conditions. So under these properties, we were able to show the following theorem. that given some desired speed and some desired distance, which satisfy this algebraic equation, we were able to show the following inequality. This is the L2 string stability requirement based on the energy of the system, energy motivated by the energy dissipation of the system, plus a term that depends on the initial conditions. Moreover, we have the L infinity string stability, which shows the deviation of the vehicle from the desired speed is less than deviation from the vehicle in front, plus some additional terms based on the initial conditions. Finally, we were able to show the following inequality, which implies the following. It implies that the manifold Vi equals Gi is exponentially stable. But what does this mean and why it is important? It means that if we define the local density to be 1 over spacing, then we can use this inequality to reduce the number of the study of the n-differential ordinary differential equations to the macroscopic LWR model. So essentially, this gives us a way to move from the microscopic to the macroscopic model. Under the same conditions, we also can prove, in addition to safety, stability, string stability, we can also prove stability. We have that for the desired speed and some desired spacing, which is given as the solution of this algebraic equation. We have that the equilibrium of the platoon is globally asymptotically stable and locally exponentially stable. This means that if we start from any point within the set, the invariant set we saw earlier, we can converge to these values, and if we start close enough to those values, we converge exponentially fast. Moreover, we have that for the ring road, we have a stronger result. We have that for any initial condition, we can converge exponentially fast to the equilibrium. Of course, again, here note that the desired distance, is based on the length of the vehicle, of the road, of the ring road, and the number of vehicles. So we saw this, we have a controller, but how do we design this function g? One very simple design is the following. We have the function g here. We have lambda to be the smaller minimum braking distance. So we take this function to be 0 as desired by the theorem for this length lambda. Then it increases linearly up to a maximum value, which is the g max here, where the vehicles accelerate fast, and then we have some dissipation when the vehicles are further apart. They also satisfy that, to also satisfy this last inequality. Now, depending on how we choose the slope of this line, we can make the transition from braking to acceleration much smoother. So for a small slope, we have better passenger comfort at the expense of larger distances between vehicles. Of course, for this function g, we can also calculate the fundamental diagram, and depending on how we design it, we can obtain different fundamental diagrams. This simple design allows us to have a triangular fundamental diagram. With designing appropriately the constants, we can have different critical points or capacity. Finally, to note here that this is for this triangular fundamental diagram is based for is due to this particular function g as designed here, and in general can have any desired shape as long as it satisfies some standard properties. For instance, it has to be on the free flow side. It cannot be larger than these values. So one way, let's see how to compare this nonlinear controller to the scenarios we saw earlier. So in the first scenario, we had the constant time headway controller where it exceeded the speed limits of the road. Here, on the other hand, using the nonlinear controller for exactly the same scenario, we see that the vehicles accelerate up to the maximum value and then decelerate again as they reach closer to the leading vehicle. These are also the spacing of the inter-vehicle distances of the platoon. They also converge to some desired value, and here are the accelerations of the vehicles. In the second scenario, we had a leading vehicle that, in an emergency situation, where it decelerated very fast to some small speed. With a constant time headway controller, we saw that we may have some negative speeds here. However, this is not the case when we use the proposed nonlinear controller. We see that the vehicles in the platoon decelerate, their speed is very close to zero, and they start to accelerate until they reach the speed of the leader again. These are the acceleration of the vehicles. Of course, here we use maximum deceleration rate for the platoon in order to avoid the collisions and we are in an emergency situation. And finally, we had a scenario where we had collisions when we use the constant time headway controller. And in this case, we see that with a nonlinear controller, the distances of the vehicles will never reach the minimum distance, which is selected here to be the length of the vehicle equal to 5 meters. Here are also the speed of the vehicles. They do not go below zero. And of course, here are the accelerations of the vehicles. This is a very simple simulation for the ring road scenario. We see here 4 vehicles that also converge to a desired distance equilibrium and desired speed equilibrium. And finally, here we see how the string stability requirement. We have, in this scenario, we have a leading vehicle with a black line that starts the platoon at equilibrium, it decelerates, and after a while it accelerates again back to its original speed. We see here that the vehicles in the platoon follow exactly the same approach without any overshoots on the speed. So these are the plots for the L2 string stability on the left and the L infinity string stability on the right. L2 string stability was the dissipation of the energy dissipation, so the first vehicle has more energy than the second more energy than the third, and so on. And on the right, we had the maximum deviation from the equilibrium position, which also shows that as we move along the string of vehicles, this dissipation decreases. So we have seen today a nonlinear cruise controller that is designed to satisfy several requirements for autonomous vehicles. We have seen that it is possible to have a controller that has no collisions. It satisfies certain stability requirements, all vehicles, meaning that they converge to the desired spacing and speed equilibrium. And also we have string stability. And finally, we also saw some macroscopic properties. Some possible extensions for this controller are, we can also include possible delays in the control action, and also to include nudging. Nudging is a virtual force that is exerted from the vehicle directly behind our vehicle. Remember that here in the controller, we only used the speed of the vehicle directly in front, but it may be possible to also use the controller the speed of the vehicle directly behind its vehicle. The thing is that when we also consider nudging, we have seen that at least in macroscopic models, we have a very strong stabilizing effect. Another possible extension is the study of the corresponding macroscopic model for this cruise controller. Next, just to pique your interest, we have seen that vehicle automation is advancing day by day. We have moved from the standard cruise control to adaptive cruise control and also to cooperative cruise control, where vehicles can also communicate with each other. So it seems that the path to full automation is more than likely in the foreseeable future. But the thing is, do we need to abide to lane-based traffic, which was designed for human drivers when we have autonomous vehicles? This is a new paradigm, a traffic paradigm that we are studying right now on lane-free concept for vehicular traffic. And here are some very initial results. We have been able to design cruise controllers for autonomous vehicles, which are based on a more complicated vehicle model inspired by the bicycle model, which is able to capture the movement on the two-dimensional surface of the road. It has the heading of the vehicle as well as the speed and acceleration. We were able to show that we can move in the two-dimensional surface without collisions and to respect the road speed limits and to converge to some desired speed. And this is only sensor-based. There are other approaches where we can have communication between vehicles. We can have also macroscopic models. Feel free to check our website for further developments. Thank you.
Okay, thank you. Thank you, Dionysis. Now we are open for questions. For audience, feel free to unmute yourself and ask questions, or you can type your question in the chat box. Okay, maybe I can start.
Yeah.
Hi, Dionysis. Excellent presentation. Honestly, I didn't follow all the mathematics derivations in the middle of the presentation, but at the beginning, we start with saying that string-stable ACC controllers might be dangerous because sometimes we end up with very short spacing or even collisions.
Yeah.
Yeah, I think the trade-off between safety and string stability is important. Yeah, I'm just wondering, collision is like the extreme case that will happen under some situations. But we have also seen some other string-stable controllers work well at a different speed level. So my question is, from your perspective, does every string-stable controller have the same issue presented, or just some super string-stable controllers at some extreme cases will lead to the unsafe problems here?
Well, most likely it's going to be in extreme cases, but there are no guarantees. I mean, if you don't design a controller if it's not designed to have collision avoidance, then you cannot guarantee that there are no collisions. Of course, I mean, even if you start very close, if you have very sudden lane changes, of course, you cannot avoid sometimes collisions. But I mean, yeah, in general, string stability, it's been shown in the past. In the 90s, I think, were papers where they were showing that string stability is not sufficient to have collisions. Yeah, collision avoidance.
Okay. Okay. Okay, nice. Okay, so Deirdre raised her hand. Deirdre, do you have a question here?
Yes. So thank you very much for the presentation. It's very interesting, also very intense. So I need to read the paper in more details. But I have two questions. Number one is, so you showed that it is possible to have to achieve stability and safety. So you have a slide showing the fundamental diagram. So I was wondering, yeah. So I was wondering that the benefits of safety and string stability guarantee. So does it have to come at the price of lower flow here?
Maybe, yeah. I mean, you need spacing to avoid collisions.
Yes.
But that depends also. That depends also on the capabilities of the vehicle. I mean, if a vehicle can decelerate very fast, then you can have lower spacing. But on the other hand, if it decelerates very, very fast, then you don't have passenger comfort. So if you want to include both passenger comfort and safety, you need spacing, which means lower flow.
Yeah, I think that's expected. So my other question is, so from the empirical experiments, we see that most of the commercial ACC systems are not stable right now. So do you think which aspect is violated in your design that they fail to guarantee the stability and maybe even the safety? Any insights? I know we don't know how to design ACC, but maybe any insight on why they fail?
Well, one way here, for instance, for this controller to fail is that you start with outside the set of, let me go back to some slides here. Yeah. In order to have this safety, we need to start our platoon to be initialized within this set, to have sufficient distance. I mean, if the distance, we have a very slow vehicle ahead and it changes lanes directly in front of you, then you cannot avoid collisions. Okay.
Oh, so the initial spacing.
Yeah, exactly.
I see.
But here, notice that if the vehicle in front is faster, you just need to have very small spacing. I mean, on the other hand, if the vehicle ahead is much faster than you, then yeah, you need much slower, then you need spacing. About this issue with string stability, yeah, it's been shown lately that commercial ACC vehicles are not string stable, but this is based on probably on the manufacturer. I mean, I cannot say why they are.
Yeah. Cool. And I assume that in the system that you analyze here, so you assume that there is no delay, but in the real cars, we do see the delay there. So do you think they also contribute to the instability?
To instability? No, I mean, what you need for the delay case, one needs to, most likely will need some slightly larger spacing. Like this, the braking distance to be slightly larger, this constant lambda. Allow me to go back to a few slides. Yeah, here. So this is the minimum braking distance that a vehicle, whenever the distance is less than lambda, the vehicle decelerates. Due to some delays, if this constant lambda is something larger, then again, I don't think there is going to be a problem for small delays. Now, for large delays, but here we talk about autonomous vehicles. So the delay is not going to be something, I guess, something very large.
Yeah, interesting. Okay, yeah, thank you very much. That's very useful.
Suyuan, please go ahead.
Okay, thank you, Theodosis, and very interesting presentation. And from my thinking, if I treat with this dangerous situation, it's safety problem, I always say the bound. But currently, you provide a very nice combination to combine all the things together. And yeah, thank you for the presentation. I just have two questions. One is about the fundamental diagram, and I just, it's I mean, for your presentation, I didn't get the spacing policy for that one, and based on the fundamental diagram, if it looks like a triangle, it may be just like it's maybe a constant time Hathaway policy. Is that a constant time Hathaway? That's my first question.
It is not a constant time gap policy. Here, essentially, the policy, let me go a few slides earlier, is actually this VI is equal to G of SI. This is the spacing policy here.
Okay.
So this G is a nonlinear function that depends on the distance. So I cannot say that this is a constant time gap.
Yes, but my question is that the fundamental diagram is look at like a triangle, right? If we look at the conjunction side, maybe if it's look like a triangle, that means maybe the time half is constant value.
This is because of the function g. Here, the fundamental diagram, the flow depends on this g, this capital G. This is the integral of this function g. If we design this g in any other way we want, we can obtain a completely different fundamental diagram and not a triangular one. This is only for this function.
Okay, good. Got it. Thank you. And my other question is about your numerical experiment. And in your numerical experiment, we can find that maybe it's just like the set of vehicles. We can see the enhancement about the string stability, but it's just a little bit, right? And just like every vehicle will copy the speed or the trajectory from its leading or speed trajectory of its leading vehicles. Could you find? Maybe in your other experiment, could you find more enhancement about in string stability, or just maybe in this dangerous experiment, we can see it's copied to each other? Because in this experiment, I can only get a little bit of enhancement in string stability.
I didn't really get your question.
Yeah, my question is...
can you further dampen the disturbance? That was also my question.
To dampen the disturbance, you mean? Like, I don't really get the question, sorry. So,
if my question is, if you it's string stable, right? And when a disturbance happened, it will need the amplitude of the disturbance maybe decrease vehicle by vehicle. But in this situations, I can see just they have the same amplitude.
You mean here?
This amplitude is enhanced, right? And if it's stable, we want to find it. The amplitude of each vehicle is just a decrease. But
here it may look that it is string unstable. That's what you mean?
Yeah, it's string unstable, but in your nonlinear controller, it's just string stable. Yeah, it's string stable, but the disturbance is equal to each one.
It's equal.
Yeah, I see it's almost equal. I have to say from your actually definition norm, I can find maybe there's some enhancement. Yeah, just like. Yeah, I can see a little bit of enhancement, but in your previous speed trajectory, I cannot find this. Maybe not very clear.
This is because different notions of string stability. This is based on the energy. This is the deviation from the speed. The left is the energy dissipation. This is the dissipation from the desired speed, from the equilibrium. That's why it does not exceed, it doesn't have an overshoot. This is why here the energy is larger for the first vehicle and it reduces.
Got it, thank you.
Okay, I saw AV raised his hand. Please
if I may intervene, can you hear me?
Yeah.
Yes.
Can you hear me? Marcos Papageorgiou. I'm a co-author of this work. So regarding the previous question, the reason why the disturbance was the same is the maximum speed, because in that example that Dionysis has shown, there is a limitation of maximum speed. And in order for the vehicles to still be string stable, behave in a string stable way, they do reach the maximum speed. I think this is not the one, Dionysis, that was with the speed going up to the maximum speed.
Yeah,
This
this
one.
one.
Yeah.
This one.
So
Yeah, this one.
this one, yeah. I mean, the point is here that, as you have seen in the previous slide, other controllers would exceed the maximum limit and would be string unstable like this, yes. And this controller makes use, I mean, does not exceed the speed limit, but makes full use of it to behave in the best possible way. That's why it looks like, you know, it's not amplified, but it's also not lower the disturbance than the initial one. It stays, but this, as you can see here, it stays below the speed limit. That's the reason why it looks like that, and certainly it is string stable. In other kinds of experiments, it would be
Exactly equal. Yeah.
it would
Now
be
I
visible
understand.
that, you know, the disturbance is attenuated.
Okay, now
Thank you.
I think I got the question. This is also because of the following definition of string stability. Let me go back here. So here, if you see, we have some amplification due to this term. This is because the system is not initialized at an equilibrium position. So this is why we get this slight overshoot. If the system was initialized from an equilibrium position, then we would have a figure like, let me go, like this one.
And my guess is that, so if we can go back to the overshooting case, exceeding the speed limit. So my guess is that it also depends on your objective function, because you only want it to be string stable so it can reach the maximum speed limit there, as long as it does not violate the stability. But if you change the objective function, say you want to further dampen the overshooting here, then I guess you could.
Yeah.
Yeah. So thank you, Marco, for the explanation. How I think there is another question there.
Yes, from AZ.
Yeah, yes, I'm here. Yeah, thanks for your presentation. So my first question is related to how would you tune your controller given different situation, like for avoiding overshooting the speed limit or avoiding collisions? Do you use the same parameters to achieve desired performance throughout your experiment?
Yeah, it's fixed. I just chose some. Let me go to the design here. So I just wanted to have. I just chose these constants here to satisfy the speed limit. Okay, this k here also gives us the deceleration rate of the vehicle, the maximum acceleration. So first I designed it to have low accelerations to also satisfy this condition, and that was it. After that, the function g is trivial, given by this equation.
Okay. Yeah, because I think maybe extra tunings of those parameters can give you a much nicer response from the vehicles, and multitasking can be a challenging thing for a single parameter settings.
Yeah, that's very true.
Yeah, and
again, if I may intervene, it's not just the tuning of parameters. You have here a whole class of different functions, which of course must satisfy some conditions that Dionysis mentioned. And you can choose any function that satisfies the conditions, which will. So, if you really want to find the best in terms of, you know, safety or in terms of convenience or whatever, then you may look not only into different parameters, but also into different functions. So there is a broad range of possibilities here, which is not restricted to parameter values, but even to functions. G.
yeah, exactly. So my second question is like how do I say it? It's But I cannot remember my questions.
All right.
So,
Dr. Lobo, you want to go ahead and give him a minute? Yeah.
thank you. So my first question is, do you envision or think it's possible to have a controller that is more than string stable, so it would dampen oscillations, but not lose capacity?
Dampen oscillation, not lose capacity. That depends. I mean, this controller, if you take this constant K as it looks like now, you can have more.
Sorry, it's just in general, not just for the controller you're presenting. It's like based on your experience, and it's an open question really to the audience.
Okay.
Do you think it's possible to get a better than string stability in a sense?
If you also want safety, no.
And that you think that can be shown, that can be proven?
Well, the thing is, to have safety, you need spacing.
Right.
So you have string stability, but you need spacing due to safety. Then you cannot have as high capacity as you might desire. I think that's the issue there, the safety.
Right.
I mean, here I talk about guaranteed safety, not in most cases, yeah.
Right.
If you just tune it down a bit, then yeah, you can have higher capacity at stronger dissipation rate.
And if I could ask if Marcos agrees, just for curiosity.
Agree with what Dionysis said? Yes, I do.
No, okay, so you agree that in general it's not possible to have a better than string stable model.
Wait a minute. I think what Dionysis answered was that the real competing is between safety and
right.
So if we restrict it to capacity versus string stability, I really have no strong opinion. I mean, I would imagine, without having a strong opinion, that you can have string stable systems and high capacity under the condition that we have strong deceleration, essentially, possibility. And under the condition that in case this deceleration possibility is actually needed, you will have, of course, reduced convenience of the passenger.
Right, yeah.
But for safety, as Dionysis highlighted, you probably need to restrict capacity. You cannot have guaranteed safety and at the same time very high capacity.
Right.
However, of course, with different designs, you can have higher capacity or lower capacity. That should also be said.
Yeah.
With different designs of ACC strategies, you may have better capacity at the same guaranteed safety.
Okay, great. And my second question was on slide 30 that you commented a bit ago. So, yeah, that's the next one, yeah. Yeah, so here I see that the follower vehicles are able to keep the maximum speed for longer, but that would mean that they're initially in free flow, right? So there's some buffer space between vehicles. Yeah. But if you're in congestion, you wouldn't see this, right?
If you were in congestion, no, because vehicles will start decelerating as they reach closer to each other because of this constant lambda I was talking about, this minimum braking distance.
Right. So in the case, so when you start in congestion, do you think all the curves here will overlap?
Yeah, I think so.
Mm-hmm. Okay, yeah, thank you for the clarifications.
Thanks for the questions.
Okay, so I need just record his second question. Let me read it out for you. His second question is about the robustness of the control law. If we have disturbance or inaccurate delayed information, how will the invariant set vary?
Well, the thing here is that we have, in addition to string stability, we have stability where, for instance, for the ring road, we have exponential stability, which is a very robust property. So disturbances, I don't think that they will create a very big issue as long as they are something bounded, of course. For the other case, for the open road, we have a global asymptotic stability and local exponential. Still, we still have some robustness because of continuity and local exponential. But I cannot say more than that. I believe that it's still going to be robust, but one needs to be careful to see this, any other properties.
I think we have one last question left in the chat box from Ali Sigu. He's asking which simulation platform we are used for the simulations here.
Oh, here I used MATLAB.
Okay. Yeah, I think it's everything is coded in MATLAB, not some specific professional softwares, I guess. Yeah, that's the answer. Okay, I think it's perfect timing. It's 12 now. So thank you again, Dr. Theodosis. Very excellent speech. I hope all the audience enjoy it. And we have a small announcement for the next 3 weeks. We have 3 ACC webinars given by Dr. Pang Zhou, Dr. Wenlong Jin, and Dr. Wang Meng from Delft. So please stay tuned, and thank you again. Hope you guys have a nice weekend.
Thank you, Hal.
Thank you.
Thank you very much for the